Hi, and welcome to this talk on advanced C programming. My name is Eskil Steenberg Hald, and I am the Swedish representative in the ISO Working Group 14. To be clear, I am a beginner in the working group, and there are lots of people there who are much smarter and more knowledgeable about C. But I've learned a lot, and I think it's worth making it a little bit explainer about all the various things in the C language that is really, really difficult to understand, and that causes people problems. A lot of what I'm going to talk to will apply to C++. However, C++ is a different language, and it has a different standard group and a completely different text. And while we're trying to keep C and C++ as compatible as possible, given that they are different specifications, there's always a little bit of leeway where they're not quite the same. And therefore, I don't want anyone to think that all of this has to apply to C++. If you want to know exactly what's going on with C++, read the C++ spec. But a lot of this will actually be the same. So, C++ and C uses mainly the same compilers. So when I'm going to talk about the compilers they do for both C and C++. So C is a very simple language, but it is a very deep language. You can really get into it. And because C is such an old language, people have, and therefore we know a lot more about C than other languages. So I want to talk about the really deep stuff. This is not a beginner talk. If you don't know C, go somewhere else. There's lots of different places where you can learn about C. This is about talking about the really deep stuff. The issues I will discuss are very rare, but when you do run into them, you will waste a lot of time because it will be the moment when you don't understand anything and just the compiler behaves in a completely inexplicable way and you are kind of lost. And it'll be very rare, but when it happens, this is a good primer. So people talk about C-like performance, about various languages that may or may not have C-like performance. And I think that C-like performance is a little bit like talking about wood-like feel or, ice cream-like taste. It's not really the real thing. So if you want performance and you want control, go for the real thing. And we're going to talk about why C is fast and why it's performant, and also why the little things that are quirky in C makes it so fast and performant. So there's a misconception that C is a high-level assembly language, and while it may be the language that is closest to assembly language, that is not really true. Compilers do a lot of transformation. What you write is not what gets executed. Compilers are really smart. They do a lot of smart things to figure out how to get the most performance out of your code. And that's why it may do things that you don't expect. Actually, CPUs do a lot of work as well. Modern CPUs do a lot of transformations and your code gets transformed in all kinds of ways. So in a way, you could say that assembly language is a high-level assembly language. Even if you read the assembly language, it will not tell you the whole story about what your code does because the processor may rearrange things, reorder things, do a whole bunch of stuff that you can't actually see. So what transformations can the compiler do? There is a rule called the as-if rule, and that means that it can do whatever it wants as long as the end result is the same as what you meant. So let's do some simple examples. Here is two assignments, x is equal to 0, and then x is equal to 1. And the compiler may say, well, I'm just going to write x equals to 1. It's the same result from these two operations. So I can just remove the x equals to 0. And this means that it's not consistent all the way through, but it's eventually consistent. The previous code was not consistent halfway through because x was not 0, but eventually it became consistent. And this is a really important thing. That means when you look at code sort of halfway through, it may not be where you think it is, it will just become eventually um, the right thing. So what's eventually? If we look at this, it is really easy to see that x equals 0 can go away, but why is eventually x equal to 1? Um, the first thing to think about when you do this is be careful when benchmarking. For instance, if you make a loop and that loop overwrites the same value, that loop may just go away because the compiler might say, well, you're overwriting the value 1,000 times. I'm just going to write it the last time. And, the under 999 times I can just throw away. So here's another example. A is equal to 0 and b is equal to 1, well, it can just say b equals to 1 and a equals to 0. The ordering doesn't matter. The end result is the same, right? So reordering is completely fair game for a compiler. However, if you run, printf hello and then printf goodbye, it can't change that to printf goodbye and then printf hello. Why is that? Because the end result is not the same. So why are these different than the previous things? Well, there's a thing in C called something being observable. So what is observable? It means that the end result can be noticed outside the program in some way. It might be writing to a file, it might be doing some I/O, it might be doing, UI or something like that. Something that someone can notice from the outside. So this brings us to a keyword in C called volatile. What does volatile mean? It means that something is observable. It is observable to something else, even though it may not look like it's observable. So let's go and have a look at this again. Okay, so here we have A and B, and we're setting them to be volatile. And then we're setting a is equal 0 and then say a is equal to 1. Now the compiler cannot just write a is equal to 1 because volatile means that the a is equal to 0 is a observable event. Something, may look at that. Maybe it's another thread. Maybe a is storing, um, you know, talking to a piece of hardware. Maybe you've given the address to, a graphics card that reads that memory address or something like that. And therefore, it cannot be optimized. So volatile is mostly used for hardware things, but it can be used for lots and lots of different things. And it basically kills the possibility for the compiler to optimize certain things. So here we have another example. We're writing x is equal to a, and then y is equal to a. So you could think, well, both x and y are a, right? So you might as well write x is equal to a, and then y is equal to x. But that's not actually true because x is volatile. X can change without it being noticeable. Maybe another thread is reading from reading and writing to x. So if we look at on the right here and say, what if there's a thread between these two lines that overwrite x? Then we don't have the same result, right? Because now y is something else than a, right? So volatile stops that because volatile essentially says, don't trust the numbers. Like the variables can change at any time. They're volatile, right? So here's another example of an optimization that a compiler may do. You write while a and then printf, and the compiler say, well, a can't change. A doesn't change within this loop, so I don't have to check a every time. I can just say if a is true, then run this loop forever, right? Because there's nothing these two are equivalent, but the one on the right is much faster because we don't have to compare with A all the time and check what A is. We could just like run forever, right? Now, obviously, this may cause a problem if A is something that does change. So therefore, you have to write volatile. If you write volatile, you say, hey, A can change. Maybe it's another thread writing to it. Maybe it's a piece of hardware. Maybe it's something that makes A change. And that prevents the compiler from doing this optimization. So the same goes for order. So here we have A and B, and we're writing first to A and then to B. Now, volatile means that this is observable, and that means we can't change order to them. We can't write B and then A. If they weren't volatile, we could change this order because it doesn't matter, right? But with volatile, it does. So what do we use volatile for? Well, we use it for hardware interaction. Like we're talking to things that, you're writing a driver, you're on a microcontroller or something like that. You're listening to a pin that may change, right? The hardware will interact with the memory and therefore you need the memory to be set to volatile. Memory mapped file is another good one. If you have a memory mapped file, another process may read or write to that file, and that means that the content of that file can change at any time. And therefore, reading the same value twice can't be optimized to one read. It has to be two different reads because maybe maybe the value changed, right? Another reason you might want to use volatile is something I call touch. So imagine you have a piece of memory, and this memory has a lock on it, and therefore multiple threads are working with this memory. And you can lock the memory and read the memory, but the moment you do this, no one else can touch the memory, right? And what if the memory has been swapped out to disk or something like that? And you turn on the lock and then you try to read a value. And now all of a sudden a hard drive somewhere has to spin up. And it takes 2 seconds for it to spin up. And then once it's spun up, then you get the data and then you can unlock. That meant you now held that lock that you should have held for microseconds. You're now holding it for several seconds. That's a very bad idea. So what you might want to do is say, I'm going to read from this address and I'm going to read from it, but I'm not actually going to use that data for anything because I haven't locked it. So it might be garbage. Somebody else might be working on it, but I'm still going to read from it. And by reading from it, I make sure that the operating system will put it in memory so that it's close by. And once it is, then I can call, lock and then read and then unlock, right? And then I know that my lock is going to be much shorter because the retrieving from disk happened before I actually locked it. Now a compiler that looks at this and say, oh, you're reading a bunch of memory but you're not actually doing it, that seems stupid, let's not do that. So it's going to optimize away that read because you're not doing anything with it. So therefore you might want to say, hey, this is a volatile read, read it even if it makes no sense to the compiler. And finally, we get to multi-threading. Obviously, other threads can impact your program. Now, there's a big asterisk here because multi-threading has many different aspects to it, and we're going to talk about that next. So here is another example of some code. So we have, we allocate some memory. We put this memory, we set this memory to a value, and then we, take this pointer and put it to a shared pointer. Now, the compiler looks at this and say, okay, you're doing these things, but wait a minute, I can just as well set the shared pointer A and then set the value. This is completely legal. This has the same meaning as before, right? Now, if this is a shared pointer, this will all break, right? So therefore, we need to somehow say that you can't reorder here, right? Because this is a multi-threaded program and the ordering here really matters. And then we get to the three things we have to care about when we do this kind of operation. We need to care about volatile, we need to care about atomicity, and we need to care about acquire and release. So volatile is the idea that if we read something, it could be changed by someone else. Atomic is the property that when we actually read or write, we have to write all of it or nothing. And if we don't, if we read a piece of data, we want to read all of that and have it be one part. We don't want to read a value that is being half written or half read because someone other thread is working on this value at the same time. And acquire and release means that when we have an interaction with another thread, things cannot be reordered. So let's have a look at that. So we look at this, we can add volatile to our little function, and all of a sudden, some things happen. Like the good thing that happens here is that the shared pointer actually gets written to, and you know that it's written to, but all the other operations here are not volatile. And that means that even if the volatile stuff is observable, what happens before and after is not, and therefore those things can be rearranged. So the volatile property here is giving us some some good properties, but it's not giving us all the properties. The compiler can still screw us over. So what we need to do is make sure that it's a atomic event. Now I write this to a shared pointer. Is this an atomic event? Yes and no. It is an atomic event on some processors like the x86 architecture or x64. So if you have a PC or, you'll be fine. A non-atomic process is something like a plus plus, because you're essentially reading a value, adding one to it, and putting it back, which means that in between those reads and writes, some other process can go in and do something, right? So, okay, so shared pointer equals a is an atomic on some processors, but there's actually instructions to use for doing this. And even if you are on a platform that can do this, actually use a function like this. So here is a function called atomic exchange, and it's basically saying exchange the value in shared pointer to a. And by saying it's atomic, we're saying don't break this up. Don't do a half written or half, read or anything like that. Do all of it at once and stop any other process from interfering with that. Now, you don't need to do that on some processors, but you do need it on some, and therefore you should always use these functions, just because if you want to make it portable, and also it's just sort of really good because if somebody looks at this code, they know, oh, this is an atomic event and it's actually visible. So even if you're exclusively working with a processor architecture where everything is atomic, or all the smaller writes are atomic, you should always use an atomic function. But then we have the rel you get on the end, and that says that this is a release semantic. It is a function that says I'm releasing some data to someone else. And what release means is that everything I did before has to happen before. It cannot happen after. If I do something after this function, it can happen before. But so I can move things up, but I cannot move things downwards. And that's a really important thing. Now, even if your compiler doesn't do this, so here's actually the rules for this. Acquire means nothing after this can be done until this is completed. And release is everything before this point has to be done. So there's an acquire and a release semantic. And essentially you use release when you give something to other, you're releasing it to someone else, and acquire when you're saying, I want to read something and I want things to depend on this, right? And therefore, the things that depend on that come after has to actually happen after you've acquired it, right? So that's important. And then there's also functions that have a full fence, and that means nothing can move either up or down. So that's an acquire and a release semantic in both of them at the same time. Usually you don't need a full fence, but it's also really nice to have it because sometimes it's just like, I don't want anything weird to happen. Let's put a full fence. Okay. And acquire and release is not just telling the compiler what to do, it's telling the hardware what to do. Acquire and release are not just, telling the compiler don't reorder this when you optimize. It's actually different instructions in the processor because the processor is wrangling lots of memory and caches and things like that. And it needs to flush all the caches so that no one else is reading from a cache, a local cache to that core that is now, has changed because someone else has written to that memory address. And therefore, it's not enough to just write and read. You actually have to acquire and release in order to flush memory. And that's really, really important. So that's why you should not read and write things and assume that another thread can read them correctly unless you're using some kind of locking mechanism. Okay, Now we're going to talk about undefined behavior, which is the bane of C, but it's also really cool, and it's also why C is really fast. So the C standard has 6 pages of listing of all the undefined behavior. The next version, C23, is going to have a lot more pages because we've actually gone through and found new undefined behavior. Undefined behavior is things where the standard says this is undefined behavior, but it's also all the things that no one has gotten to. So there are things in that the specifiers have simply not included, and therefore by definition they're not defined and they're undefined behavior. And therefore there's no actual complete list of undefined behavior because you can actually come up with new things that aren't defined. And therefore this is a bit wobbly. So, for instance, it's undefined behavior to call the exit function more than once. This is an example of the weirdness you can encounter where you read this and you say, why would anybody ever do this? Well, C is an old language. People have tried a lot of things, and they've realized actually you can make multiple threads that call X at the same time. And what should a compiler, what should an operating system do? And they've decided, well, it's up to the operating system. We don't define that kind of weird thing. So there's a lot of corner cases like that that don't really matter. And C is a deep language because all of these corner cases have been explored. And lots of other languages probably had these, but they haven't, gotten, where it's a 40-year-old language more. It's a 50-year-old language soon. So all of these things have, somebody has, found this issue, reached out to the standard and say, hey, what is this? And they've documented and said, oh, it's not defined. So that's a reason why there's so many pages of just listing the undefined behavior. So why isn't it defined? Like, why don't we just make up an answer to what should exit do if you call it more than once, right? Well, it's really powerful for a couple of reasons. The main thing is that it lets compilers do really smart things. Another reason is that it means that C can be implemented on, without a huge amount of work. So for instance, if you implement exit, you don't have to care what happens if the end user calls exit more than once, which means that exit doesn't have to be thread safe. And that's just a little bit of saving time when you're implementing a new operating system or a new system. You can just skip that. There's no requirements you have to follow. And that's one of the reasons why C is implemented a lot of times and why it's on every platform and you can use it everywhere. But let's talk about optimizations because this is where things get kind of interesting. C is fast because it is undefined. So what does that mean? Let's have a look at an example. Let's look at this code. We take X, we multiply by 2, and then we divide it by 2. Now, if you have, basic school math, you can say, this is completely useless. This doesn't do anything. It multiplies by 2 and then divide by 2. These two operations cancel each other out, and the question then becomes, can the compiler optimize this away, right? And the answer should be yes. But then you start thinking about it and say, wait a minute, if X is an unsigned integer, then X can actually wrap, which means that X times 2 might actually be smaller than X. And then if we take that value and divide it by 2, we get something completely different, right? So it's not so clear cut what this answer really is. It depends on what X is. So if this is an undefined, if wrapping is undefined, which it is for signed values, then we can optimize this away. Because the compiler can say, well, maybe X times 2 will become so large that we can't store it, but that's undefined behavior. I don't have to care about that. I'm going to assume that doesn't happen. And therefore, I'm always going to assume that X times 2 is twice as large and that X times 2 divided by 2 is the same as X, and therefore I can optimize this away. So therefore, now you can start seeing that the fact that um, signed integers have an undefined wrapping behavior, means that you can actually optimize this. Whereas an integer with an unsigned modifier is you can optimize this. So the fact that we have something be undefined creates this opportunity to optimize, right? So here's another example, right? You take an array of 5 values, and you say x, right to 0, right? What can we say about this code? Well, we can say that x has to be 0, 1, 2, 3, or 4. It can't be any other number, right? It can't be 58, because if it is 58, then we're writing somewhere we're, outside the array. So we can actually look at this code and we can make an assumption about what x actually is. Now, if we now write, if we couldn't do that, we could write this. Like, if I write this code and say x has to be less than, if x is less than 0, then we can't make that assumption again, right? We can't, x could be 5 billion here, right? It could be anything, because we're checking if it is below 5. Now, this gets to the idea of assumed absence of UB, assumed absence of undefined behavior. The compiler knows that the language can get into a state of undefined behavior, but when it does, it can do anything. Like anything can happen, and therefore it can assume that the code is well written and that will not get into the state. And that means if I write this code, a 5, and then write to x, and then I say if x is larger or equal to 5, print hello. The compiler can look at this and be like, well, x can't possibly be equal or larger than 5, because then we have undefined behavior. And since we can assume that the code will never get into a state of undefined behavior, we can assume that x will never be this, and therefore we can optimize away this whole printf. This printf should never happen. If it happens, the program is already broken, so it doesn't matter, right? This means that a compiler can assume that undefined behavior is unreachable. So unreachable is a compiler term for saying that this is a state that cannot happen. And here's another example of this. If we take a divided by x, well, if x is 0, we got to divide by 0, which is an undefined behavior. Therefore, just by looking at the first line of this code, we can say x can be lots of things, but it cannot be 0. And therefore, if we do an x is equal to 0, it can say, well, this is impossible. So, let's not add this code, right? Here's another example. I'm shifting a value. Let's assume this is a 32-bit value. I can't shift it 32 bits or more because that's undefined behavior. And therefore, the compiler can actually remove this whole test, right? This one is a bit specific because compilers don't actually do this optimization, but they are completely within their rights to do so. There are built-in functions in GCC and all major compilers, LLVM, called a built-in unreachable. And what that means is that you put that function somewhere, and then the compiler can assume that it cannot get to that point. Visual Studio has something called assume, which is a function where you can say, for instance, assume a is less than 5. And then it will just assume that and work as if all other possibilities are not possible. So what might you want to use unreachable for? Here's my favorite example. So let's do a switch. We have a switch with 0, 1, 2, and 3, right? There's 4 different possibilities in this switch. And we're using A as our switch. Now, we can transform that into an array of function pointers, right? And this array would have 4 different values, 0, 1, 2, and 3. But the problem is that A can be anything, right? We don't know what A is. And therefore, we have to have an if statement first to say, hey, is A less than 4 and bigger or equal than 0? If so, we can do this lookup. If A is 5,000, then we don't want to do the lookup because we're looking up somewhere wrong in memory and, things go badly. So this is sort of what the transformation that the compiler can do and what they actually do. So if we now add to our switch a default saying unreachable, we're basically telling the compiler nothing else will ever happen. A will always be 0, 1, 2, 3, and that's it. There's no other possibilities. And therefore, the compiler can look at that and be like, well, if I already know that A can't be anything else, then I may just run this function and do a lookup, and I'm just going to assume that A is the correct value. If A is not a correct value, all hell breaks loose and I'll read somewhere wrong from memory and, anything can happen really. But since the user has told me that this is an unreachable, I'm going to trust the user and say, okay, it's unreachable, therefore I can move along and not have to do this test. So here's actually, a problem. Some compilers actually look at this function and says, well, this function has a divide by 0 in it. It has a bunch of code before and a bunch of code after. But if this function is ever called, then it will be a divide by 0, which means undefined behavior. And therefore, I can assume that this function will never even be called. Because if it is called, I can do whatever. And therefore, it can replace this function with unreachable. And that means that, the code that calls this now has an unreachable. And that code can do a whole bunch of optimizations that assume that whatever state is required to make this function be called, that state can never happen. And this can really cause a lot of weird bugs where code that isn't related to this bug we're seeing here starts behaving very, very strangely because the compiler starts optimizing with the assumption that the A divided by 0, is your way of saying unreachable. Personally, I think this is quite bad from the compiler designers, but it is the current state of C, so beware. So here's a very common example that people do. They have an integer a and they want to add 1 to it, but they don't want to do so if it's going to wrap. So they say, hey, if I take a plus 1, is the value larger? And if it wraps, it should be smaller, right? So only add it if it's larger. And the compiler looks at this and say, if you take a and add something to it, of course it's going to be larger, right? Because I don't have to care about wrapping. Wrapping doesn't exist. It's undefined. So I'm going to assume it's not going to wrap, and therefore I can assume that a plus 1 is larger than a, and therefore going to remove this whole if statement, right? And this means that it's actually kind of hard to figure out if something wraps, because anytime you test for wrapping, the compiler is going to say, well, this test is superfluous because, of course, nothing ever wraps, right? So here's my favorite example, which is actually code that I've written in production that caused some really weird stuff. So we have a function, take two unsigned shorts, A and B, and then we have an unsigned int. And just to be clear, the unsigned short are 16-bit and the unsigned int is 32-bit, as you would expect. You multiply A and B and put it into X, and then you say, hey, is X larger, has it the highest bit set? And if so, print out that it is, the output is larger than the highest bit set. Otherwise, it must be lower, right? And then you call this function with 65,535 twice, and you get this output where it says that 4 billion something is actually smaller than 2 billion something, right? Makes no sense. And you're saying, this is very strange. I'm using unsigned, which have all the wrapping behavior is defined. There's no undefined behavior in this as far as I can see. What is going on? Well, what's actually going on is this. If we look at the multiplication, the multiplication gets transformed into an integer. And this is called promotion, where the hardware may not have a 16-bit add thing. So it says, well, I'm going to move them to a 32-bit add thing because that's the hardware I have. And I need a 32-bit value that can store the full range of A and B, right? Whatever A and B is, it has to fit. And it says, well, an integer, a signed integer, fits all of A and all of B. Great. So it promotes these two, and therefore it multiplies A and B as signed integers. Now, once it's done with that, it says, oh, you want to move it to X? I better turn it into an unsigned integer, right? So then it turns it into an unsigned integer. Now, the thing it figures out is like, hold the phone here. A and B sort of the multiplication of A and B used to be an integer. And that means whatever we move to X can't possibly be larger than the largest integer, right? And therefore, when we get to X is greater or equal to largest bit, we'll say, well, it can't be because we know that X comes from an integer and integers can't go that big. So therefore, this whole if statement, we can figure out in advance what's going on, right? So therefore, you get this. It removes these lines of code and just prints out the value. And this is obviously not what you're expecting because it is wrapping, and the wrapping is, it wraps to a very large number. It does what you think it does, but since it has been signed int at one point, the compiler does this. If this looks scary to you, it's scary to compiler developers too. Compiler developers, they try really hard to optimize and make your code fast, but they also don't want to break your code. They really don't. And they don't like getting, mails from people where they complain about, oh, your compiler destroyed my code. So it's actually sort of a back and forth where there's a fair bit of optimizations that are possible, but that would simply break too much code. So yeah, here, beware, unsigned types can be promoted to signed types if the value fits. Okay, so because just because they can optimize doesn't mean they will, is a good thing to know, but it doesn't mean, they won't they won't actually optimize in the future, right? They can optimize in the future because they were always allowed to, and that may break your code. So looking at your code and say, well, it breaks maybe some rules, but it's working for me, is a really bad idea because you may break everything in the future with a future update of a compiler. So, I showed this already. It does currently optimize, divide by 0. It looks at this and say x can't be 0. It does not look on the right and say x can't be larger than 32. I think they do this because they assume that people who do bit fiddling know what they're doing. But honestly, I don't know why there's a difference in these two. But currently there is in both GCC and LLVM. So, at the moment of recording of this talk, who knows about tomorrow? So here's another example. We take x, we write to it, x is a pointer, and then say, hey, if x is null, printf hello. Well, this can't happen because if x is null, we've written to it already, it should crash everything, right? So therefore, we can just remove this whole if statement. Well, it gets a little bit worse than this. Have a look at this. Now, we're saying if x is equal to null, then printf error, right? And then we write to it. Well, a compiler will look at this and say, wait a minute, this if statement could happen before or after x because they don't actually interact, right? X is the same before or after, and therefore what order I do these two doesn't matter, right? And since you're eventually going to get to x is equal to 0, um, you're writing to whatever x is pointing to, and therefore x can't be null, and I can remove this thing. Because no matter what happens, you will be writing to null if x is null, and therefore, anything that happens before or after doesn't matter, right? So this is really scary because now you're writing, you thought you wrote a test here that checks if X is null and prints out an error, but the compiler just goes ahead and say, well, since X can't be null, I'll remove that error message for you. This is called time travel, where the bug actually happens before the error happens, right? So the write to null happened after the bug, right? Because the removal of the error message happens before. So you can notice a bug before it even happened, which is quite strange. But if you think about the rules of undefined behavior and you think about the rules of as is, this totally makes sense, even though it can truly scare you when you encounter it in the wild. Yes, a bug may be evident before it happens. So let's talk about uninitialized values, which is a fascinating little thing in C. So let's look at this function. You have int a, which is not initialized, and we're going to check if a is 0, we're going to return 0. If it is not 0, we're going to return 1. Now, guess what this function will return? Like, what does this function look like if you compile it in LLVM? It will look like this. It will just return. It won't even return 0 or 1. It will just return. So what the hell is going on? A value that is uninitialized is in something called an indeterminate state. And an indeterminate state is not just that we don't know what the bits are, it can be outside the combination of bits. So here's another example of what that means. Here we're reading, we're allocating a piece of memory. It's volatile, just so we can read from it multiple times. We say, hey, if this buff is null, return, right? So we know we have some memory. We have a real piece of memory here. And then we're reading some from that. And then we're reading from it again, the exact same thing. So we're C1 and C2. And then we're comparing C1 and C2. Now, obviously, if you look at this, you say, well, C1 and C2 has to be the same because they're coming from the same source. Well, that's not actually true, because they are indeterminate values. And therefore, the compiler can either optimize this away completely, but more than that, some operating systems will actually not give you memory when you call Malik. It will just give you the addresses. And when you read from them, they will not actually assign you the memory. The assignment of memory will only happen when you actually write to it. And that means that there are processors or operating system architecture where you could allocate some memory, get a pointer, you read from that, so buff 0, and you have a piece of memory that you read from, but you haven't tagged that as written to yet. And then between these two C1 and C2 lines, the processor goes off and runs some other program, and that program says, I need a lot of memory. And then the processor may give that other process memory that was assigned to our program, because you haven't started writing to it, so it's not yours yet. And therefore, it gives some other programs your memory that happens to be the one you read from in the buff. And therefore, it switches back to your program, and your program is like, hey, I'd like to read from buff 0 again. And the operating system, oh yeah, you need some memory here. Let me go get some memory for it. So it goes and gets a new memory buffer and puts it in this address and lets you read from it. Except now it's a different memory buffer and you get a different value, right? So this is really, really scary. And therefore, you should not assume that values that you haven't initialized are static and dependable. Let's have a look at another example. So here we have a type def struct. We have an integer, 32-bit. We have a char, one byte, and we have a short 16-bit, right? And if you know anything about C, you will know that in this structure, you will have some padding, right? So let's initialize our struct. So we're writing A and then B and then C, right? If we look at this, we will actually have 3 instructions because it will write 3 values. If we do this and say, hey, mem set the whole thing to 0, and then write A, B, and Z, right? Same thing. And this looks like it'd be like, okay, so you just made the code slower because you're setting the memory first, and then you're writing A, B, and C again. That's really stupid. Well, actually, this turns out to be a lot faster. So why is that? Because in this case, the whole structure is 64 bits, and the compiler can issue a single instruction that sets all 64 bits at once. But since there was a little bit of padding, it doesn't want to touch that piece of padding. But once you set memset, you've already set what that padding should be, and therefore the compiler says, well, I'm just going to set the whole thing, and I'm going to compress all this to one write, right? So this code is actually faster. Now, padding is interesting because it is undefined. The compiler doesn't have to do this. The compiler can look at this original thing and say, well, there's padding, but I don't care about padding. I'm going to turn it into a 64-bit value and just do a single write. Except a lot of programs break when you do that because a lot of programmers don't do the right thing. So, the compiler is a little scared and it doesn't dare to do that. So therefore it'll say, well, if you do a memset first, then I know what you're doing. I can trust that you're not depending on this padding, and therefore I can go. But padding is wobbly, right? If you read or write a value, that value may be faster to write as a larger value. Let's say you're writing, an 8-bit value. But if that value is next to a bunch of padding, maybe you'll write a 32-bit value and just overwrite the padding, right? And therefore, that padding may change without you noticing it, without you actually accessing it, because the compiler can optimize that. Some compilers do this, not all. Now let's talk about the memory model. This is the really scary stuff or interesting stuff. Let's have a look at this example. So here we have a function that sets an array, right? We have 2 integer pointers, one storing the array and one storing the count, right? So we're making a basic for loop and we're looking through this. We're going through this count and setting all the arrays to 0. Okay, so the compiler looks at this and be like, ha, I see you're nulling out a bunch of things. It'd be really nice if I can just replace it with a memset. Memset is very, very fast. It's optimized on all platforms and so on. So this would be the fastest things we can do, right? The problem here is that what if you wrote this? You call this function and you say, here's my array. I'm going to set the 42nd value to 100,000. And then I'm going to use the array to null it out. But I'm going to say the 42nd value is how long I want you to go. So when this happens, when you now call this, the loop will run for 42 values, and then the array will overwrite the counter. And the counter will be set to 0 and will stop counting. And that means because of this, you cannot optimize the previous function into just a memset because you can't read the value of count just once and then assume it's going to stay the same because you're writing a bunch and that might overwrite that value if that value happens to point to the same thing as you're writing to, right? This is a huge optimization. If the compiler somehow could avoid doing this and make it we're talking about sometimes 100 times faster performance, right? So this is something the compiler really wants to do. So if you write this, a count, one integer, this is super easy, right? This is what the compiler wants, right? There's no pointer, read every time. And you may see looking at this, this is how I would write it. I wouldn't write to an integer and read the pointer every time. That's stupid. This doesn't concern me because I'm a pro programmer. I know what I'm doing. I wouldn't do this stupid thing. Well, let's show this. Here's a struct. In the struct, you have an array and you have a count and you run. This is much more what somebody would actually write. But again, the pointer to the struct may actually be the pointer to the array too. The array and the struct may be the same piece of memory, which means that overriding the array may influence the struct, right? So how do we optimize this? So the compiler would really like to determine if a pointer aliases. Is two pointers pointing to the same part of a memory, the same allocation? This is an integral, like, important goal for any performant compiler to figure out. So C has some rules to help the compiler do this. And the first one is type aliasing. So let's look at this function. Here we have a float array and an integer count. A compiler can look at this and say, well, you have a pointer to a bunch of floats and you have a pointer to a bunch of ints. Since they are pointing to different types, they cannot possibly point to the same thing. They must point to different things. Therefore, the compiler can look at this and assume that the array does not influence count. And you can read out count once and then just null the array. This is an assumption the compiler can do. And if you do this, if you write this and you have these overlap and you expect it to pick up on that overlap, you're in for a surprise because it may not do that. So here's an interesting example of this. We have a union, we have an unsigned integer A, we have a float B. We want to know what the bits for this float value is, right? This is very, very common C, idiom. So we take convert B is equal to, something similar to pi, and then we write out what this value is. This is fully legal C. Nothing wrong with this. Look at this. Now we're doing almost the same thing, except we're saying I'm going to get a pointer to an unsigned integer. And I'm going to take the pointer from the convert A. So from the unsigned integer, I'm going to read out that pointer. And then I'm going to write to B. And then I'm going to write out whatever P is pointing to. And you look at this and you say, well, it's exactly the same, right? It's the same value. But the compiler looks at this and says, wait a minute. Convert is of a type union. P is of a type unsigned integer. Therefore, they cannot possibly influence each other. They are working with two different types of memory. Therefore, they cannot overlap. And therefore, a compiler can, for instance, say, well, I'm going to print out, do my printout before I do the convert B equals 3.14. Because the order of those doesn't matter, because the convert and P have nothing to do with each other. Those two functions are interchangeably in order, right? We can change order for them. And of course, if we do change order for them, the program has a completely different meaning, right? So this is an example of where type conversion can really create some weird things. Now, in honesty, a lot of compilers will figure out what you're doing here, and they will not make that assumption. Compilers are just as scared as you are of this, and therefore they try not to make use of this, even if they can. So this may not be a problem on your machine, but again, it is allowable. So if you make this mistake, a future version of a compiler may not be so kind. Okay. There is an exception to the type rule, and that's unsigned char. Unsigned char in C parlance is kind of just memory, right? It doesn't have a type quite, right? It's just bytes that you do things with, and therefore you assume that everything aliases with unsigned char. So an example is memcopy. When you do memcopy, it takes unsigned char, and it's just assumed that memcopy copies all kinds of memory, not just unsigned char, and therefore a memcopy will influence memory that may be floats or ints or whatever have you, and therefore the compiler always assumed that unsigned chars aliases to everything. And that may make unsigned char really slow in certain ways, but it also stops a lot of the truly weird things. Like otherwise, things like memcopy would be actually very hard to implement. Okay, there's also actually an explicit alias restriction you can do where the user says, I'm making a promise that two things will not alias. And here we have an example of that. So we have the same function here, but we're having a keyword called restrict. And by using the restrict keyword, we're saying this value will not alias with anything else. And that means that the compiler looks at this and says, well, in regular world, I could not optimize this. But since you've made the promise that these two are restricted, I can go ahead and optimize. Finally, we get to provenance. And provenance, essentially, where does memory come from? Memory objects do not exist in relation to each other, right? If we think of memory, a lot of times we think of memory as this very long address space, right? And you get sections of it. And if you go outside of an address space, outside of an allocation, you'll eventually get to another one, right? Because they're all in one big row. This is not strictly true. It's usually true in the hardware sense and in the operating system sense, but it's not true in C. And this means that different objects, since they cannot be in relation to each other, you can do some clever optimizations. So if you try to guess or compute the relation of two objects, that is not allowed. And the compiler may, completely remove that code if you're trying to do something fancy. Because obviously, if you have two addresses, you can compute where they are in memory and compare them. That's, quite clear, in practice. But since it's not allowed, compilers may do some weird things. So let's have a look at this. Here we have int a and b. A and B are, on the stack, and then we have a pointer. So we're going to take the pointer from A. So we're going to say, where is A? And then we're going to step one pointer forward, right? And we're going to say, hey, is P now pointing to B? Right? Because A and B are in the stack, and we don't know what the relationship of these two are, but, let's guess, right? They're probably next to each other. A's probably followed by B. So let's try this out, right? So now we're going to print out what this answer is. So we're going to say, hey, if these are equal or they are not the same, right? If you do this, the compiler may look at this and be like, well, P comes from A. It's pointing to A, and you can move around in A, but you can never get to B because A and B are two separate things. They are living in their own spaces. And if you travel around A, you can get somewhere, but you can never get to B. And therefore, P can never point to B. It's not possible because they are different things. And therefore, the compiler can say, aha, since they can't be equal, I can remove this whole if statement. And of course, when you print this out, you may get two addresses that are exactly the same, and the compiler states that they're not. Because they're not really. They're pointing to two different things, even if the addresses in the hardware are the same. They are actually working in two different address spaces. Another one of these things is that dead pointers don't exist. So if you have a pointer to something, obviously if you free that pointer, you can't operate on the object you're pointing to. The pointer is dead. But the actual number, the pointer, is also sort of dead. So let's have a look at that. Here's an example. I'm allocating some memory. I'm freeing that memory. I'm using that memory for something. And then I'm allocating some new memory, right? And I want to make sure that the address of the new memory isn't the same as the previous. I just want a piece of memory that has a unique memory address that isn't something I just freed. So what do? I compare A to B and say, hey, if this new piece of memory happens to be the old memory, go ahead and allocate some more memory and then free the memory I just allocated, because now the new allocation is obviously going to have a different address, and I can overwrite B with C, right? Great. The compiler can look at this and be like, okay, you freed A. That means that A is nothing. It can be anything. Like the value of A doesn't matter anymore because it doesn't point to anything. And once it's had that opinion, it can look at the if A is equal to B and say, doesn't matter at all. I can just remove this. I can say that A will never be B, and I can remove the whole if statement, right? And this is actually a problem because there is a class of bug called ABA. And ABA is a very particular bug that is probably the scariest bug you'll ever find. And it has to do with, especially when you do lock-free multi-threading. And the structure goes something like this. You have one thread that allocates A, and it shares A to someone else. It's now shared. Thread number 2 reads A and says, okay, A. And then thread 1 swaps out A for B and frees A, right? So now free, and then thread 1 again allocates C, which happens to be identical to A, and then swaps out B for C, right? And now we swap back to thread number 2. And thread number 2 says, hey, I've just made a bunch of math and calculations that depends on the value being A. Is the value still A? And if it is still A, I can now overwrite A with the result. And this, of course, destroys the world because now thread A never noticed that B and C happened, because it thinks that between its reading and writing, no one else has changed the value. But of course, thread 1 has changed it twice. It's just that it changed it to something else and then it changed it back. And the fact that it changed it back to a pointer that happened to be the same as the original one causes this, mayhem. So one way you can get around this is to turn pointers to integers. If you turn a pointer into an integer, you can use that for comparisons, even after the pointer is dead. You can actually compare two pointers from different objects. That's allowed. You cannot do a larger and then smaller than because they don't have a relation to each other, but they can be equal or not equal, right? So therefore, generally, turn pointers into integers in order to be able to do comparisons after pointers are dead, but do not turn integers back into pointers because pointers are weird. Pointers may have interesting properties. A pointer may not just be a memory address, it may be a fat pointer that includes information about allocation size, memory types, all kinds of weird stuff. All of that is allowed in the C standard. It's not very common, but it is allowed, and therefore doing integer math and then turning it into a pointer is something you should be, I really, really urge you not to do. Malik is another one that is fair game for optimization. Malik can be removed by the compiler if the compiler doesn't think you're allocating memory for any useful, task. So here's an example that we looked at before. The compiler can look at this and be like, well, you're allocating some memory, and then you're freeing some memory, and then you're allocating it the same size of memory. I can just keep the first allocation and just use that memory over and over again. Because why would I do multiple allocations when I already know that I'm allocating the same amount of memory? This is stupid, right? So now the compiler will actually, make sure that B and A has the same pointer because it will remove these instead of what you thought you did, which was carefully make sure that A and B aren't the same pointer. So here's another example of something that may screw you over. Let's allocate some memory and see if it returns null. And if it does, then we don't have any memory and we can, put some error out there. And, if there is memory, we'll just free it. compiler looks at this and be like, I can assume that memory is allocatable, and therefore it's not going to return null. I can just remove this whole function, right? So are you guys scared yet? C can be scary, but it is a really powerful language. It is worth using. And I want to give you, to end this, some survival tricks to help you as a C programmer. Obviously, watch this talk a bunch of times, but more than that, there are some other things you can do. Do not use bit fields is a good idea. Bit fields are weird, they're not fully defined, and especially the promotion rules for bit fields are obtruse and difficult to understand and very easy to make mistakes. Variable length arrays should never have been added to C, in my opinion. They cause all kinds of problems. They're not implemented correctly everywhere. The standard actually no longer requires them to be implemented, so please stay away. Don't be clever with a preprocessor. A lot of people like to use the preprocessor for lots of clever things. Don't do that. Make clean code. Use the preprocess for includes, use it for defines, and sort of stop there. Use a good debugger and learn it. I use Visual Studio. I think everybody needs a visual debugger and not something like GDB, which is very capable but is so hard to use and so slow to use that it's not really useful. If you use Visual Studio, use QuickWatch. QuickWatch is a way for you to explore memory. You can read memory and see what it is. You can even write your own paths to memory. It's very, very powerful. Use sanitizers and use Valgrind, tools like that that allow you to find bugs. There's lots of different projects out there. You may not want to run them all the time, but every once in a while it's really good to run them. Use gflags in Windows. So gflags is a utility that Microsoft gives out, and it gives you a bunch of kernel options. So one of the options is that all allocations you do will get their own memory blocks, and it will get the end of those memory blocks, and then it will get a memory block right after that that is write protected. So if you ask for 16 bytes, you'll get the last 16 bytes, and if you overwrite by 1 byte, you will get a segfault instantly. Uh, Turning this on will make your computer a mess because everything will start crashing. So it's not really a good thing for your sanity. Luckily, Microsoft runs this on everything. So usually Microsoft software works quite well. So if you need a browser, use a Microsoft one. But this is actually a really, really useful thing to turn on every once in a while. But you can also write your own memory debugger. It is not that hard. I have written my own memory debugger, part of my library Forge. It looks roughly like this. What you do is you wrap malloc and realloc and free or whatever other functions you're using into macros that take file and line. And that means you can record every time you do an allocation. You can record when you free, where you've freed memory, where you read memory, and you can do things like keep track of how much memory you've allocated. You can, make a printout that says you've never freed anything from these allocations. Super easy to find memory leaks. You can also over allocate all your allocations and put some magic numbers at the end of them, and therefore you can check those magic numbers, make sure they're not overwritten. If they're overwritten, you can put a break or give an error message. It is super useful. Once I implemented this, I actually stopped using a lot of other tools. Avoid dynamically addressed arrays on the stack. If you have arrays, generally if you overwrite on the stack, you will cause all kinds of mayhem because you will overwrite variables and it's hard to debug. If you overwrite memory on the heap, on the other hand, is usually a lot easier to diagnose. So if you do put values in arrays on the stack, try to do things where you actually don't access them using a dynamic number that may go out of range. You can also read the MISRA C standard. This is a standard for how to write C in safe and secure environments. They have lots of good ideas, and you don't have to adopt all of it, but there's definitely good ideas that will give you some ideas from people who are really, really smart and thought a long time about how to write good C programs. Use a compiler explorer. I use Godbolt. So does most of the C working group. You can put in any C code and see what the compiler does. You can switch between different compilers. Learning a little bit of assembler is really useful in order to figure out what a compiler does. And just being able to test things yourself is very, very useful. And before you send a bug report to your favorite compiler, you may want to try a different compiler or a few different compilers to see if they do the same thing, or things like that. If they all do the same thing, it's probably your fault. And by the way, you can read what all the compiler options do. If you read through what all the optimization flags do, you'll have a pretty good idea of what your compiler does. There's some things in there that may surprise you. My favorite one is GCC. If you have optimization level 2 or higher, you will actually have null, writing to null will be defined. It's no longer undefined behavior, which means that just changing the optimization flag will actually change what platform you're developing for, which to me is a somewhat dubious choice. And those kinds of things will catch you out, right? So read up on that, know what your compiler does. It'll take you half an hour to read through it, but it'll be well worth it. Read the book, Whatever Programmer Should Know About Memory. That will not take you half an hour. It is as deep as you can ever go in how memory works, but that tells you a lot about how computers work. And it's so valuable. And I can't recommend this book enough. It is truly, reading this book is the difference between, a real programmer and a dabbler. So I really, really recommend this one. And then just good luck and have fun. C is supposed to be fun. Programming is supposed to be fun. So yeah, have fun with it all. This is me. I want to thank everybody for watching. You can reach me on social media on @Kelsolar, which is my professional Twitter account, and then my personal Eskil Steenberg. You can also find my website at kelsolar.com. There's also gamepipeline.org, where you will find a lot of my source code for my memory debugger and lots of projects. And if you just want to read some C code that is, I hope, fairly well written, you could go there. You can also watch my talk, How I Program C, which is very long, but it gives you a lot of ideas about style and such things. So I want to thank everybody for watching, and I hope to make a new video in the not too distance. So thank you very much.